In previous lecture, you saw that we were looking for the steady state response of a circuit to sinusoidal input. So our goal is finding the steady state response to sine and cosine waveform. Okay. So the first approach was using Laplace transform and finding, so the first approach was using Laplace solution and finding y of t, or first y of s. So finding y of s, consequently finding y of t, and remembering that this y of t is our total response, so which is equal to y of the transient response plus the steady state response. So then we can remove or throw away the transient portion and keep the steady state response as our answer. The other solution is using phasor. So if you remember, one of the constraints of phasor was that the response that you get from phasor analysis is basically only the steady state response, and it only shows you the response from the response of the circuit when you have sinusoidal input. So it seems a good solution. So another method is going to be using phasor transform in order to get the steady state response to sinusoidal waveform, but there is a problem with phasor, and the problem is that every time that you have a new source into your circuit, you have to do all your analysis again. If you want to change the frequency, because your impedances are related to the frequency, so if, for example, if you change your frequency from 10 to 100, then your inductor impedance will be 10 times more. So all the components most of your circuit components are affected by frequency. So it means that for every single frequency, you have to analyze the circuit completely again. That's the problem with this approach. But other than that, it can help you to find a steady state response to sinusoidal waveform easily. But here, I want to show you a third approach. So the third approach is using h of s to find directly what we are looking for. So the h of s has a main benefit that you cannot get that from phasor solution, and the benefit is that you don't need to reanalyze the circuit every single time that your frequency is changed. So you can just use the same approach, and it's much easier, and it doesn't need everything to be calculated from scratch. So I'm going to show you, and then you can compare the solution with phasor solution as well. Okay, so let's see what we are looking for. We know that the circuit has a transfer function of h of s. And we can apply any input to the circuit, and then by multiplying the input Laplace transform, we can get y of s. Now, we know in this scenario that our input is, in time domain, our x of t is equal to a cosine of omega t plus theta, which means we can find our x of s. What I'm looking for is y of s, and that's equal to h of s multiplied by x of s. Now, the x of s is a sinusoidal, and I showed you that in general, you can show your sinusoidal waveform with a magnitude, phase angle, and frequency. These are three different parameters that can change when you're applying a sinusoidal input to your circuit. Okay, so I know that this is my time domain signal that will be applied to my circuit, so I can describe its So my input is in time domain is equal to a cosine of omega t plus theta. Now what I need is x of s. So in order to describe my x of s, first I'm going to describe my x of t. Let me delete this here. So first I'm going to describe my x of t in this form. X of t is equal to a cosine of theta cosine of omega t, I'm expanding this term, minus a sine of theta sine of omega t. Now, as you can see, this a cosine of theta and a sine of theta are constant values because theta is fixed, a is a coefficient, so these are constant number. So if I'm looking for the Laplace transform of this in order to describe x of s, what I have to do is that I have to describe the Laplace transform of cosine and then the Laplace transform of sine. So x of s, which is the Laplace transform of what I have here, is going to be equal to a cosine of theta multiplied by the Laplace transform of cosine of omega t, and that's equal to s over s squared plus omega squared. Okay, so what I have here, what you can see here, is the Laplace transform of cosine of omega t. And then for sine, I'm going to have, let me write the coefficient here. That's a sine of theta. And then for sine of omega t, I'm going to have omega over s squared plus omega squared. Okay, so I can merge these two because they have exact same denominator, which is equal to s squared plus omega squared over, and on the top I have a cosine of theta multiplied by s minus a sine of theta multiplied by omega. Now, in order to show how it works here, I need to have an h of s. So I'm going to show you how we can use h of s directly to find our steady-state response to a sinusoidal input. I'm going to use an example, the example that we use at the beginning of this topic, so I can consider the h of s of the circuit here for this case. So let's review what we had in our example. We had a circuit, and in our circuit we had Vg as input, which we are considering this Vg to be sinusoidal now. And then we had this circuit with 10 to 6 over S for the capacitor's value and 250 for the resistor in series with the inductor and 0.05 S for the inductor. And you saw that the transfer function which described the voltage of capacitor with respect to the input is equal to 1000 multiplied by S plus 5000 over S squared plus 6000 S plus 25 multiplied by 10 to 6. So this is what we have as our transfer function, which describe Vc over Vg. So this is our h of s, which we need for this in order to find our output. Okay, now I'm gonna rewrite this, but I want to bring the denominator into its factor. So our h of s can be described as 1000 multiplied by s plus 5000. And if I break my denominator into its factor, I'm going to have s plus 3000 plus j 4000 multiplied by s plus 3000 minus j 4000. Now, if I multiply this h of s by x of s that I have here, I'm going to have this y of s. This y of s is basically the result of x of s multiplied by, here I have h of s. So as you can see, now I can describe my output because I know what is my transfer function and what is my input. Okay, now let's go to the next step. If I want to know what is my answer, I need to break this y of s into partial fraction. What are the terms in my partial fraction? In my partial fraction, I'm going to have four partial fraction. 2 of them are because of the roots I have for h of s, and 2 of them are because of the roots of my inputs, which is j omega and minus j omega. Just quickly to remind you here, j omega and minus j omega are coming from here, so the j omega plus minus j omega are the roots of s squared plus omega squared. Okay, so let's do the PFE here quickly. So applying PFE, what I'm going to have is 4 small fraction or partial fraction which describe my y of s. The first one, I'm going to call it as k1 over s plus 3000 plus j 4000, and then k1 conjugate over s plus 3000 minus j 4000, and then I'm going to have k2 and k2 conjugate over s plus minus j omega. Okay, so these are, again, the results of these 2 partial fractions are here because of x of s, which is my input, and these 2 partial fractions appear in my response because of h of s, which is a transfer function of the circuit. Now, I want to see which partial fraction will end up being transient response and which part will provide the steady state response of the system. Okay, let me remind you how we can do the Laplace inverse for this fraction. So if I want to write the partial fraction for this one, I'm going to go with green. So if I want to describe the partial fraction of the first 2 terms, it's going to be 2 multiplied by the magnitude of k1 e2 minus 3000t. The 3000 is what I have here, and then multiplied by cosine of omega t, and omega is 4000 t plus theta of k1. So this is what I'm going to have because of the first 2 terms, which are the result of h of s. For the second one, it's going to be 2 multiplied by the magnitude of k2 multiplied by e to 0t, and then cosine of omega t plus theta of k2. So here I don't have any real part in my root. Because of that, e to at is going to be e to 0t. So basically it means that I don't have this term, it's just 1. This term is equal to 1. So now you can easily see that this term that I have here, the first one, is transient response because of this e to minus 3000 t, and the second term does not have any dying factor. This dying factor is equal to 1, so it basically doesn't damp the response. So the response that I have here, this portion of my response, is my steady state response. So what I can do to make my calculation less is that I can ignore calculating K1 and K1 conjugate. I know that at the end I'm gonna delete this part of my answer. I'm gonna throw away this portion of my answer. So why I need to calculate this portion at all? So what I'm gonna do is that I will calculate only K2, and then the y of t that I have at the end, so the y of t that I'm calculating in this form, is the steady state response, and that is going to be equal to 2 magnitude of K2 multiplied by cosine of omega t plus angle of K2. Now the question is that what is this K2?